All right, welcome to Chapter 19, Lecture 2, Pre-Lecture Video 2. Today we'll be talking about alternative reactions to enolate reactions with nucleophiles. That is, there's somewhat of a secret we've been hiding throughout the time we've been talking about enolate alkylation reactions or enolate acetylation reactions and so forth, and that they can be messy sometimes. So today we're going to talk about two alternatives to this enolate chemistry we've been learning, one of which is the acetoacetic ester synthesis and a closely related malonic ester synthesis. These are used to come up with selectivity problems for traditional conventional enolate chemistry that we've been talking about. A second strategy is the use of enamines to get around some of these selectivity issues. And so we'll talk about what we mean by selectivity problems here in a second. But by the end of this video, you should feel comfortable with these alternative syntheses and the mechanisms by which they proceed to generate selective formation of CC bonds alpha to carbonyls. All right, so let's start with a little bit of review. Back in Chapter 16, we learned about alpha alkylation chemistry of enolates. The mechanism for which looks a little something like this, wherein our base deprotonates the alpha CH bond to a carbonyl. This undergoes SN2 alkylation with an electrophile, say something like methyl iodide, to give the alkylated product. But what we didn't tell you is that there's a little bit of a hitch with this problem, this reaction. And that is our product can form an enolate that is thermodynamically more stable than our starting material. Our product can also undergo deprotonation to form a new enolate, like this one shown here. And this can occur using the enolate we started with before or orthoxide base. Now, you should be able to understand why this product we drew here might be a little bit more stable than the initial enolate we drew. The enolate of our first alkylation product here will form a more substituted enolate, and that's a thermodynamically more stable enolate. And so this can lead to complications in the reaction outcome, wherein we get a mixture of products. And as an organic chemist, this is not good. You want a nice reaction that gives a single product and 100% yield. And this reaction is often not that. So chemists have developed ways around this to generate these important products, but without some of these sort of practical limitations that this reaction often exhibits. One of these tricks that chemists have developed is called the acetoacetic ester synthesis. This synthesis involves the use of an acetoacetic ester, something of this form here. It doesn't have to be an ethyl ester. It just has to be an ester of pretty much any sort. You'll often see things like ethyl or methyl esters, though. And a base, such as sodium ethoxide, and in this case, an alkyl electrophile, an allylic electrophile. This results in the formation of a new CC bond, shown here. And then the next step is to remove the ester via basic hydrolysis and then decarboxylation with acid. This yields the monoalkylated product in high selectivity. And so the key take-home message here is that the added ester is a group that can be used to control the selectivity of alkylation, that is, give a monoalkylated product if we so choose. But then importantly, it can be removed to give the same product we might think about using enolate reactions. Say in this case, we could think about enolate reaction of acetone and allyl bromide using some sort of base like sodium ethoxide. Now, we just talked about how this reaction on the right is likely to be non-selective. However, this acetoacetic ester synthesis is quite selective. Indeed, it requires another step, this sodium hydroxide and HCl step, but it really is quite efficient. So how does this reaction work? Well, the first step, as you might expect, is to use our base to deprotonate this much more acidic CH bond of the acetoacetic ester. This CH bond has a pKa of approximately 10 or 11. And its pKa is much lower than that of, say, acetone, because that charge is shared in resonance between the two carbonyls of the ketone and the ester. This results in a much more stable anion and therefore a more acidic CH bond. This deprotonated acetoacetic ester is also a great nucleophile. It can react with something like allobromide to afford the alkylated product selectively. This will afford the alkylated products such as this. And this product can be converted into the desired alpha alkylated ketone by basic hydrolysis of our ester and then the acidic decarboxylation. Treatment with base will hydrolyze our ester, and then reacidification with hydrochloric acid will yield this alpha acetic acetoacid. As discussed in chapter 17, this compound can undergo decarboxylation to form the enol. The enol then undergoes tautomerization to afford the product. The key advance here is that these acetoacetic esters are much more easily monoalkylated, or if you want, dialkylated. However, this comes at the cost of having to do multiple steps. And so the storic enamine synthesis is designed to avoid this process. And this is something that we'll talk about in a few slides. This hydrolysis acidification sequence is also something that can be used to synthesize symmetric ketones from Claisen condensation reactions. And so here we have a starting material that could be synthesized through the Claisen reaction of ethyl propanoate. That would be this molecule here. If you don't know how this product could form under basic conditions with the Claisen condensation reaction, I would encourage you to pause the video and take a look and show yourself how to do that. But this is useful for generating some of these symmetric ketones, because the Claisen reaction is best for generating the self-condensation products where there are no selectivity issues. So this reaction would proceed via hydrolysis of the ester. This is something we talked about in chapter 18. To give this product here, reacidification will generate the acid. This acid can undergo decarboxylation through the mechanisms we discussed in chapter 17 to give the enol. And the enol quickly isomerizes to the ketone product. So again, this is identical as the previous slide. However, it's worth noting that Claisen self-condensation products can generate these symmetric ketones selectively through this added sequence. There's a variant of this reaction called the malonic ester synthesis. Here we have diethylmalonate. And this reaction proceeds much the same as the acetoacetic acid synthesis, except in the product, we end up with an acid as an ester. However, this reaction is quite difficult to control for the synthesis of an ester, so it's much more likely that you isolate the acid. And we'll talk about why that is as we work through the mechanism. So if you're this mechanism is overall quite similar to the acetoacetic ester synthesis that we just talked about a few slides ago. And I encourage you to pause the video and to work through this and to give your best guess for what's going on, because it's highly related and this would be a good chance to test your knowledge. So once you've worked through it, hopefully your mechanism looks something like this. Deprotonation of the acidic CH bond in between the two carbonyls affords the deprotonated 1,3-malonate, diethylmalonate, this compound here. This is a strong nucleophile that can then react with our electrophile, the allobromide. To afford the monoalkylated product. This monoalkylated product, in contrast to a lot of enolates, is overall less reactive and can be formed somewhat selectively. So we don't have this overalkylation problem. While the CH bond in between the two esters is indeed still acidic, it's not as good of a nucleophile once deprotonated, and we can selectively monoalkylate. Now, if you wanted the alkylated diester, such as this, you could stop here. However, in most cases, people want the monoalkylated free acid, or sometimes the monoalkylated free ester, this compound here. And so the next steps are to hydrolyze the ester with a base, and then to acidify the resulting acid. Sometimes you'll see H3O, H2O, and this leads to typically this diacid compound shown here. If you're careful about it, you might be able to form a monoester, monoacid, and then upon heating this up, this reaction decarboxylates. That is to say, it loses carbon dioxide to afford the monoalkylated product. And again, the synthesis takes advantage of the different reactivity of the diester in that it's easy to stop the reaction at a monoalkylation. This is not true of the corresponding enolate chemistry that we might think of using to make this compound. One last thing to comment on is that in these decarboxylation reactions, it's a very good idea to count your carbons. It can be very easy to add or to drop a carbon throughout this process. So I'm going to highlight where the carbons in our product come from. These two here are these two here. And then the other carbons in our molecule come from the allyl bromide. That is this compound here. And I'll highlight these over in the product as well. All right. And so it's a really good idea to go through and check that the carbons you're supposed to be missing are indeed missing and the ones you added are indeed there. All right, so the malonic ester synthesis and the acetic acid synthesis are closely related solutions to the monoalkylation problem of this enolate chemistry. And they're clever ones, but they're not perfect. They're stepwise. They use strong bases, strong acids, and so forth. And so back about 70 years ago, people started to think about other ways of doing this chemistry. And so a very popular strategy developed by a chemist named Gilbert Stork was the use of enamines. And so enamines, we talked a little bit about in chapter 16, but enamines are like the nitrogen analog of enols. So an enol is an alkene with an oxygen off of it, with an OH off of it, and enamines have a nitrogen off of an alkene. The most important property of these enamines is that they are nucleophilic at the carbon, at what used to be the alpha carbon of the carbonyl. This is precisely where we wanted to add our alkyl groups in the previous example, or using just standard enolate alkylation chemistry. It's important to note that enamines are much more nucleophilic than enols, and they are much more reactive. So the way that they form is through a standard amine condensation mechanism. In this case, this 5-membered nitrogen compound is called pyrrolidine. And the lone pair on these reach out and attack our cyclohexanone. This forms the tetrahedral intermediate that we're so used to seeing, and we need to adjust the protons here. Another base in solution, say another equivalent of pyrrolidine, could come along and deprotonate the ammonium ion from this addition. This would result in this pyrrolidine cation as well as our anionic intermediate. This can then deprotonate our base to afford the hemiaminal product. Shown here. The lone pair on the nitrogen are able to drive down and kick out the hydroxide as a leaving group. This nitrogen lone pair are better able to do this than, say, an oxygen. And this leads to the key intermediate we're going to talk about, the aminium. All right. So this is the iminium ion, and if we had protons off of our nitrogen, we might deprotonate them to get to the imine. However, this cationic character of this, in this case, it would be formally on the nitrogen, but is in resonance with a carbocation-based depiction. This increases the acidity of the alpha proton here. And this can be deprotonated by base in solution. I think in this case, it makes the most sense to draw pyrrolidine doing this reaction. To afford the enamine product. These enamines have a key resonance structure that tells us about their reactivity. The depiction shown here is the best resonance structure. However, we can resonate those electrons from the nitrogen down, and those kick over the enamine electrons. And these show us why it is that these compounds are nucleophilic at their alpha carbon here. And that is because we can resonate an anion down there in a logical way. Again, this is not the best resonance structure, but it depicts the reactivity of enamines. Right, so these enamines are very useful synthons in organic chemistry. That is, they're very useful reagents to affect a certain type of transformation we want. And since they're nucleophiles, they react with strong electrophiles, such as this allyl iodide here. And they do so with alkyl electrophiles like allyl iodide through an SN2 type reaction here. And this generates an iminium ion, because the lone pair on this nitrogen fall down to stabilize the resulting carbocation. All right. Now this product here is brought to be the desired ketone or aldehyde by hydrolysis. And this hydrolysis mechanism is the reverse of the imine condensation that we learned in chapter 16. Strong alkyl electrophiles aren't the only type of electrophile that will react with enamine. To further demonstrate the synthetic utility of these reagents, we can see that again in a alkylation hydrolysis sequence here. An enamine will react with what's called an alpha halo ester. They will also react with acid chlorides to make substituted or acylated compounds. So if we took acetyl chloride here, our product would be this iminium ion, which upon hydrolysis would give us a 1,3-diketone. All right, so these are incredibly useful, and they react in a lot of ways like enolates. They're not quite as strong in nucleophiles, but they're still very useful. They can react, as I just showed, with alpha halo esters as well as acid chlorides on the bottom here. Now, all of these two solutions to this enolate alkylation problem does not mean that it's impossible to selectively alkylate and enolate, or to use enolate selectively in other reactions. One key element of this is that you choose the right base. Lithium diisopropyl amide is one such base that effectively and quantitatively deprotonates the alpha CH bond of a carbonyl. And one thing that's been known for quite some time is that it's very important to prepare the LDA in a rigorous fashion such that its concentration is known precisely. And so to prepare high quality LDA, typically what you do is you take the corresponding conjugate acid of LDA, that is diisopropylamine. and you store it under a nitrogen atmosphere. Many of these bases are so strong that they'll react with the water in the atmosphere, or they'll react with the oxygen in the atmosphere. And so you have to take great lengths to keep them away from reactive chemicals until you're ready to add those reactive species. And so dinitrogen is an inert gas, and so you store many of these chemicals under dinitrogen to protect them from the side reactions that we'd like to avoid. And then what you do, because diisopropylamine is a very, very, very weak acid, we have to add an extremely strong base. One of the most common extremely strong bases is called butyllithium. It's a C4 carbanion with a, I'll draw it in this sort of form here. We have a lithium plus and a carbon minus. This is one of the few bases strong enough to quantitatively deprotonate to the lithium diisopropylamine to make lithium diisopropylamide. I'll draw it again as this sort of ion pair. The lithium definitely interacts with the nitrogen, and there is some element of bonding there, but the exact nature of that is outside the scope of this class. And if you have this high quality lithium diisopropylamine, this can really make your life a lot easier in terms of controlling the chemistry of the enolates you make from it. So that is, this is then used, say, to deprotonate the alpha proton of a carbonyl. And it does so irreversibly because the pKa of a carbonyl, such as cyclohexanone, is about 20. And the pKa of our base's conjugate acid is about 35. So that's a huge difference between the pKa's of the two acids in question. And so it quantitatively forms the desired enolate. As so.